Welcome. We'll continue our theoretical probability examples with number 4. A bag has 9 marbles labeled A, B, C, D, E, F, G, H, I. One marble will be randomly picked and its letter recorded as the outcome. So we'll start by listing the outcomes in our sample space S. So every possible outcome, and this set of outcomes we will indicate here with set notation. So a brace there is also called, I call it a curly bracket, but a brace here will enclose our outcomes. So we could get the marble lettered A, B, C, D, E, F, G, H, or I. And I'll close that brace, and that is our sample space. Next, it says list the outcomes in the event choosing a vowel. So I'll just call that event V. So our vowels, I'll circle them up here, A, E, I. So those outcomes in event V, A, E, I. And you can tell my braces are looking a little messy. So on Alex, it'll actually put these braces in for you, but I'll just try to make that look a little better. There we go. All right, and then we're going to switch to probability. So what is the probability of choosing a vowel? So P of V, probability of that event. So our classical probability or theoretical probability would say, look at the number of vowels as our numerator and divide by the number of possible outcomes in our sample space. So in this case, we have 3 vowels and we have 9 possible outcomes. So 3 over 9. And that is a perfectly acceptable answer. But if you're asked to reduce, you want to reduce. And so we can there look at both numerator, denominator are divisible by 3. So either answer, totally acceptable. But if you're asked to reduce, go ahead and reduce. Okay, let's try another one. So we have a number cube labeled from 1 to 6. I'm going to stop there for a moment. Number cube here, just another way of saying a die. So we've got a die and it has 6 faces. We're going to roll it and record the number rolled as the outcome. All right, so our sample space. So when we roll the die, we could either roll a 1, a 2, a 3, a 4, a 5, or a 6. And then list the outcomes in the event, rolling a number from 3 to 6. So I just called that event E. So we could get 3, 4, 5, 6. Any of those outcomes make up the event. And then the probability of that event. So one more time here, theoretical or classical probability says count the number of times the event occurs, the number of outcomes in that event, and divide by the number of outcomes in your sample space. So event E up there consists of 4 numbers out of a possible set of 6 outcomes. And again, perfectly acceptable answer, but if you are asked to reduce, we can go ahead and reduce. Okay, so next what we'll do is take a look at the relationship between this theoretical probability and the experimental probability we learned earlier, and we will address what's called the law of large numbers, which we'll get to in a second, but let me jump in with this example first. All right, so I have a dial, a spinner, a dial. It has 6 equally sized slices. 2 are blue, 1 is red, and 3 are yellow. The dial is spun, stops on a slice at random, and we are going to spin that dial 10 times, and the results are shown here in our table. Okay. So we're going to start with the theoretical probability of landing on yellow. So continuing our theoretical probability, we look at our sample space. So we're going to look at our spinner, not the experiment, look at our spinner and see what the probability of yellow will be. And I'll just do Y for yellow. So again, theoretical probability counts the number of outcomes that are yellow over the number of possible outcomes in our sample space. So over here on the spinner, since we're looking at the spinner, we have 6 slices possible. So those make up your sample space. So that's going to be our denominator. And out of those 6 slices, 3 of them are yellow. So in theory, the probability of yellow, 3 out of 6. And I'm going to go ahead and write that in decimal, 0.5, and I'll switch that to a percent, 50%. So there's a 50% chance in theory of landing on yellow. Now for part B, it says, what is the experimental probability of landing on yellow? So when we actually conducted the experiment of spinning that dial, these were our results. So in this case, the number of spins, so these are the frequencies of what occurred. So when we did our spins, we landed on red twice, we landed on yellow 8 times, we landed on blue 0 times. So if we were to add up all those frequencies, this will be our N, the number of trials, and there's the 10 dial spins. So coming down to our experimental probability, the formula was frequency over N. So yellow occurred 8 times out of those 10 spins. And again, I'm going to write that in decimal. That's 0.8. And I'll switch that also to a percent, 80%. All right, so in theory, we should have gotten yellow 50% of the time, so half the time. And that should make sense. 3 out of the 6, so half of the dial outcomes are yellow. But when we actually did our experiment, we got yellow a higher percentage of the time than 50%. So what the law of large numbers says is that the larger the number of trials, the greater the likelihood that our experimental probability will be close to the theoretical probability. But with a small number of trials, like 10, these values can be quite different. So the law of large numbers would say if you spun that dial instead of 10 times, say 100 times or 1,000 times or 1,000,000 times, you would have a better chance of this probability coming out to 50%. So that is our law of large numbers. All right, let's see this in action with another example here, number 2. All right, so a state lottery board. Give us a little more space there. All right, a state lottery board is examining the machine that randomly picks the lottery numbers. On each trial, the machine outputs a ball with one of the digits 0 through 9 on it, and they then put that ball back into the machine. The lottery board tested the machine for 200 trials, and these were their results. All right, so these balls in the machine have one of those digits. So I'm just going to indicate here, when we look at our machine, that will tell us our sample space. So there are how many balls in the machine? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 balls in the machine. And when they did their experiment testing the machine, the frequencies are given for each ball that was output. So the ball outputted, or the machine outputted a 0 ball 12 times, the 1 ball 19 times, the 2 ball 20 times, etc. So over here on the end, if we were to add up all those frequencies, that would be our 200. And we could check, but it does say they tested the machine 200 times. And then let's look at the actual question here. So A, from the results, compute. So we're going to start with experimental probability. So compute the experimental probability of getting an even digit. All right, so for experimental probability, we're going to look at our table. those are the results of the experiment, and we want to know the probability of getting an even digit. And I'll just do E for even. All right, experimental probability is F over N. So in our table here, all right, so these are the different balls and probability of even. So even digits. So I'm pretty sure everybody's good with 2, 4, 6, 8 are even. Sometimes people do ask me about 0, but 0 is also an even number. So those are the balls that have even numbers on them. And we are going to figure out the frequency of times we got an even. So I'm just putting a little F down here. So these are the frequencies, how often the machine put out one of these balls. All right, so the machine picked the 0 ball 12 times, plus the 2 ball 20 times, plus the 4 ball 24 times, plus the 6 ball 18 times, and it picked an 8 ball 15 times. So out of 200 outputs, we add our numerator there, we will find we got an even ball 89 out of 200 times. Since I'm going to be doing a little comparing, I'm going to go ahead and change that into decimal. So that's 0.445. And let me also write that as a percent. So 44.5% of the time, the machine shows an even numbered ball. All right, so they're testing the machine, and they'd like to ultimately decide if the machine is fair. So it picks these digits with these balls with an equally likely chance of each. So that's where we're headed. We want to see if the machine is fair. So let's see in theory, what is the probability of getting an even digit? So based on the experiment, we know what happened. But now let's find out in theory, what is the probability of getting an even digit? So theoretical probability, we look at the machine itself and look at the number of even digits, so the number of balls that have even numbers, and we divide it by the number of balls in our sample space. All right, I'm just going to put down my denominator. So there's 10 balls in the machine. And of those balls, so out of those 10 balls, 1, 2, 3, 4, 5, 5 are even. Sorry, let me spell even correctly. 5 are even. All right, so in theory, we should get out of 10 balls, 5 out of 10 times, we should be getting an even, and that is 0.5 in decimal, or 50% of the time. So if the machine were fair, we should expect it in theory to pick an even ball 50% of the time, half the time. All right, but when we did our experiment, we did not get an even 50% of the time. We got an even ball 44.5% of the time. So we don't have an exact match here. The part C says, assuming the machine really is fair, so even and odd digits are equally likely, 50%, 50%. If that machine really is fair, then the larger the number of trials, so the more trials we do, the larger the likelihood that our experimental probability will be close to the theoretical probability. All right, and there you have it. So that's our relationship between theoretical and experimental probability and the law of large numbers.